Morning, everybody. Can you hear me? Hello?
Yes, sir. Good morning.
Okay. Somebody say something so I can make sure that you can hear me. Can I say something so I can hear you? I just want to verify that I can hear you. Someone say something.
Good morning.
Hello, bro.
Hi.
How are you?
Okay, good. All right. So let me check if I have my holds and everything. Okay, let's start. We're going to continue our series of lectures on training neural networks. And we have seen two things so far. What were the key things that we have learned about training neural networks? Does anybody remember? Can you remind me? What were the things that we've seen about training neural networks? Anybody? What is this business of training a neural network? Anyone? What are we trying to do? Minimizing the error between what and what. So we are minimizing the divergence between what and what. Again, can you remind me? Are we minimizing the divergence? Okay, so are we minimizing what is the target or what is the objective that we want to minimize actually? Anyone? What is the true objective? Do you remember this? Someone? The loss, the approximate function, what is the true objective we want to minimize? The true objective. So the expected divergence, that is the true objective, right? The shaded area that we saw. What we want to minimize is the expected divergence between the function and the network output. What is it that we actually minimize? We minimize the empirical error, which is the average divergence over the training data instances. These two are not necessarily the same. And so, but still, figuring that we want to minimize the average divergence between the training data and between the predicted and actual values at the training samples, we end up with a loss function. This is an empirical estimate of the expected divergence. And this empirical estimate is a function of the network parameters. How do we minimize this empirical estimate, this loss? Anybody? How do we minimize it? Anybody remember this? Be quick, guys. I mean, we're taking up time. Gradient descent, right? And what is it we need to what is it that gradient descent needs? It needs, it needs derivatives, gradients. And how do we compute the gradients? Anybody remember that? How do we compute the gradients? Backpropagation. Perfect, right? And so we saw that neural networks are universal approximators. They can model anything provided they have the right architecture, but we must train them to approximate any function. We specify the architecture and learn the weights and biases. Networks are trained to minimize the total loss on a training set. This we do through empirical risk minimization. And we use variance of gradient descent to do so. So the gradient of the error with respect to the network parameters is computed using backpropagation. So here's what we had. We defined a loss, which is the average divergence between the actual output of the network and the desired output of the network. It depends on the network parameters. And so in the gradient descent algorithm, we initialize all of these parameters and iteratively find the derivative of this loss with respect to network parameters. The transpose of the derivative was our gradient, the way we defined it. And we keep moving the estimate of the network parameters in a direction that's exactly opposite to this gradient. And the reason we go against the gradient, why do we take a step against the gradient in the negative of the gradient? Why do we do this? Why is it minus gradient? Anybody? Do you remember this? Why is this minus and not plus? Because the gradient is the direction of increase and you want to go in the direction of decrease. And then, so we saw the vector derivatives, right? Now, we saw how we can compute the derivatives in the vector format. The output of each network influences the affine value at the next layer, the output of each layer. And this affine value in turn influences the output of that layer. So the derivative, which connects yk minus 1, the output of the k minus 1th layer, to zk, which is the affine term at the kth layer, is the weight of the kth layer. I'm including the biases here. And the derivative of the activation of the kth layer with respect to the input to the activation is the Jacobian of the activation. So in the backward pass, we keep going back through the layer, through this chain. At each step, we right multiply the current derivative by whatever is on top of this edge. So when you go back from yk to zk, you just multiply the derivative of the divergence with respect to yk by this Jacobian, the right Jacobian. When you go back from zk to yk minus 1, you right multiply the derivative of the divergence with respect to zk by this weight matrix. And in between, you want the derivative of the divergence with respect to the weights and biases here. The derivative with respect to the bias, you're computing the derivatives. The transpose is the gradient. So the derivative of the divergence with respect to the bias is simply the derivative of the divergence with respect to zk. The derivative of the divergence with respect to the weights is yk minus 1. Okay, so this should have been yk minus 1 times the derivative with respect to zk, right? That was what we found in the last class. Now, do you remember all of this? Everybody, do you remember all of this? Okay, so while at it, let me actually fix this error because I tend to, these get, okay. And so let's move on. Here is the overall training algorithm. You iteratively update the parameters within each iteration. You go through all the training instances, pass the training instance through the network in the forward pass, compute the derivatives going backward in the backward pass. You compute the average derivative over the training instances, and then adjust all parameters against this derivative in the negative of this derivative. So that was our training algorithm, right? So here is our first poll. And let's see if I have this poll here. We just spent 8 minutes on the recap. It should be faster than that. So I'm giving you only 30 seconds for this. Okay, 10 seconds, guys. Let me end this poll. Here's what you guys thought. Stop sharing. Can somebody answer this? Which is the derivative for the weight WK? Anybody? Which is the derivative for the weight WK? We just saw this. Can someone answer me this? The first one, right? I don't know why so many of you got it wrong. I just literally just showed you this. The derivative with respect to WK is YK minus 1 times the derivative for ZK. I even made a correction over here. And you should have been observing this. And so this is the correct answer, right? Please pay attention because, otherwise you will be lost. Let me continue. So backprop, or rather gradient descent using derivatives computed using backprop, does that always work? This is something that we want to consider, right? So we're going to look at convergence of gradient descent on rates and restrictions. We'll look at Hessians and acceleration in Nastrov and alternate approaches. We're going to consider all of these in the next couple of classes. But today we're going to focus mostly on the convergence of gradient descent. Meaning, does Backprop. So there's a bit of a poor use of terminology. People use the term backprop to refer to gradient descent, where the gradients are computed using backprop. So the question is, does gradient descent find the correct solution even when it finds the actual minimum of the loss function? This is the question we want to answer. So to go back, remember when we trained the network, what we wanted to train the network for was to minimize the classification error. If you wanted to perform classification, the classification error looks like this. There's an ideal target function, which might be this one, goes here, predicts 0 till here, and then predicts 1 from here on. But then the actual network computes something different, 0 until here and 1 over here. And so there is a difference, there's an error between the network output and the desired output, and we can quantify the error by the total number of classification errors that it makes. Now, in this situation, if the network makes an error, we know that we want to move this threshold, but the data itself doesn't tell you which way to move the threshold. If I move the threshold from T1 to T2, the overall classification error doesn't change. And so to account for this, we made a change. We saw this in the last class, or the class before that, we changed this manner of this activation, which goes directly from 0 to 1 to a more continuously graded one of this kind. Then what was the second change we made? Instead of simply counting the errors, we counted the total distance between the desired output and the actual output of the network. And if we take the lengths of these dotted lines as instead of the count of error, we found that if we move this function backwards, this total length actually reduces. And so this tells us that we have to keep moving the function backwards, and this will reduce the error. So we saw this 2 classes ago. Now here's my question. Will minimizing the error using the smoother activation function and this continuous variant of the divergence actually minimize classification error? So we'll minimize the length of these, total length of these dotted lines, actually minimize classification error. What do you think? Yes or no? Is it guaranteed? So, Arnav, why do you say no?
If we were to have a lot of red dots on the far right, then the graph would keep shifting left to minimize that error.
So, right, so this guy we note is just a proxy for this one, right? And so let's say I had like 1 million training points or a very large number of training points out here. So, I had like a large number of training points out here, or even out here. So if I have like an extremely large number of training points, each of them has this distance is going to be infinitesimally small for each of these training instances. But cumulatively, the distance is going to be so large that in an attempt to minimize that distance, these data instances will keep pushing this curve out left. And you may end up with a curve of this kind. And so minimizing the error using this continuous curve is not necessarily going to minimize the classification error. That makes sense? Everybody remember this? Right. So here's a different way of looking at this. And this is a very nice paper by Brady and Sloaney some way back when. So it answers this question, is backprop, or rather gradient descent using backprop, always right? In classification problems, the classification error is a non-differentiable function of weights. The divergence function you minimize, which is this one, the average length of these lines, is only a proxy for the classification error, and minimizing the divergence function may not minimize classification error. So here's an example. Let's say these are my training data. And are these classes, red and blue classes, are they linearly separable? What do you think? Are these classes linearly separable? Yes or no? Yes, right? And so I'm going to consider two error minimization methods. One is the perceptron learning rule. The perceptron learning rule actually uses the threshold activation and counts error. The other is gradient descent with the smoothed version of the activation function. So both of these should be able to find this decision boundary, right? So regardless of whether you use this guy, the perceptron rule, or this guy, where we use the continuous activation function and the differentiable divergence, both of them should find this decision boundary. So both backprop and perceptron algorithms will find the solution. But now, for the same data, I'm going to add one data point, a spoiler. So let's say, for instance, that I add this guy as a spoiler. So this is a red dot. So if I add one extra data point over here, where will the perceptron, are the two classes linearly separable in this case? Yes or no? Yes. Where will the perceptron rule find the decision boundary now? Where will the perceptron rule? It's going to draw a line of this kind, right? This is your linear boundary, correct? So the perceptron rule is going to find this decision boundary, because this is what linearly separates it. What about the gradient descent method, where we're using the proxies for the classification error? What will happen there? What do you think? What would happen to it? Anybody? Because you have so many of these data points, right? So if I'm using so many of these data points, since the loss is the average divergence for all the training data points, this one guy is going to contribute very little compared to all of these guys. And so when we minimize the divergence, it will change the boundary, but not very much, because this guy doesn't have enough influence compared to the mass of data points out here. Similarly, if I had a different data point, if I put a spoiler out here, the perceptron rule is going to learn this dotted line as the decision boundary, because this one actually separates the two classes. Whereas when we're using gradient descent backprop, we're using the proxy for classification error, which is the divergence. Again, remember, the divergence function we have is a proxy for the classification error. And the average divergence is not going to change very much, because this is just one point, and there are so many of these guys. And so maybe when you use the minimize the loss, instead of this decision boundary, it's going to learn this one. So why does it say for bounded W? If you let W go to infinity, then it will indeed find this boundary, but you won't. So also, if I add
Perfect.
spoiler over here, right? Then the perceptron rule is going to learn this guy. Gradient descent is going to find this one, right? Or if I have a spoiler over here, the perceptron rule is going to find this guy. The gradient descent is always going to find this one, right? And so what we see is that the perceptron rule, which does a perfect job, is always going to give you the correct answer. Whereas gradient descent, which minimizes the average divergence, may in fact give you the wrong answer. So clearly, gradient descent doesn't find the optimal, the class of the boundary that minimizes classification error every single time. Is this a good thing or a bad thing, in your opinion? What do you think? Is this good or is this bad? Good. Why is this good? Why is this good, right? So it's not sensitive to outliers. Here's what happens. The perceptron may change greatly on adding just a single training instance. It will fit the training data very well. So it has low bias because it fits the training data very well. But then it has high variance. I can just move one single data point and the solution can swing wildly. Whereas our backprop-based method is not going to be so sensitive to a small number of data points. And so it prefers consistency over perfection, meaning it's a low variance estimator at the potential cost of bias. That makes sense to everybody? Yes, no? Yeah. And so Aditya, to answer your question, we are going to use a divergence function which is continuous and differentiable. You could always, I mean, even your classification error is a form of divergence, but it's not differentiable. So the ones that we use, which are smooth and continuous, the Kullback-Leibler divergence and so on, those things will have this property. And they can make errors. So they have some bias, they may have bias, but they have low variance. They don't get changed. They are not sensitive to minor changes in the training data. So what do you mean by cost of bias, Rishabh? Over here. So this one, okay, the potential cost of bias, meaning over here, look, in this case, it's actually misclassifying one data point, right? So that is the bias. It's actually not doing the perfect job. The answer is going to be shifted with respect to the optimal answer, which is the dotted line. But in exchange, you find that the boundary itself is not changing a whole lot. The variance is low. Did that answer your question? Right. So basically, it's a low variance estimator at the potential cost of bias. Now, that was for a single perceptron. If you have an entire network, then the network is actually going to have captured nonlinear boundaries of this kind. And again, if I just add one spoiler over here, you don't want this network to swing around and give you this boundary. And so even the larger networks have the same issue, that they will not be changed massively by a small number of outlying data points. So they are low variance estimators, and that is a good thing. So Backprop will often not find a separating solution, even though the solution is within the class of functions learnable by the network. And this is because the separating solution is not a feasible optimum for the loss function. So one resulting benefit is that a Backprop trained neural network classifier has lower variance than an optimal classifier for the training data, because the optimal classifier will always find the solution that works, but that may not be what you wanted to do. You wanted to find something that doesn't get perturbed hugely just because you added a little bit of noise to your data. So did this make sense to everybody so far? Right? So, Ejulu, remember the perceptron learning rule always finds the linear separator if the data are linearly separable. You remember that? We did that several classes ago. And so that's why it would, if you were just counting classification error, if you're always minimizing classification error, then this is what would happen. You'd always be following the dotted line. If you use the proxy for the classification error, you'll be following the solid line. And so while the proxy is not a perfect proxy for classification error, it actually is a good thing because it lowers the variance of your estimator. And so here is your first poll. Let's see if I can launch this poll. It's a short poll, 30 seconds. Yes, the optimal classifier could overfit, meaning it's chasing the data. Okay, 10 seconds, guys. This was easy. All right, let me end this. And this was a short question. You should not have had needed so much time. Here's the correct answer, right? I'll go back and let's see. What do you guys think? Minimizing the differentiable loss function will minimize classification error. True or false? False, right? That's what we just saw. And that's a good thing. Now, okay, I mean, this should have been highlighted. Now let's go on and look at the next issue, the loss function. Now, the example in the statements earlier assumed that the loss objective had a single global optimum that could be found. And so the statement we said about low variance estimator actually assume that you found this global optimum. But what about local optimum? Your loss function can be ugly. It can be like this with many little values, right? So what does the loss function itself look like as a function of network parameters? It turns out we can't really say. It's a very ugly function. And there are many hypotheses about what the loss function looks like. So one popular hypothesis is that in large networks, you have many more saddle points than local minima. So these guys, you have many little dips. They're all local minima. Gradient descent can end up in these little holes. And you have a global minimum, and the gradient descent can miss it, right? But in large networks, you also have, you tend to have things like these, where if you came in this direction, this is a minimum. But if you came in this direction, it's just a slight pause, right? Or something like this. This is a saddle point. In this direction, it's a minimum, but in this direction, it's a maximum. So these kinds of points, saddle points, they tend to abound in your loss functions. And so your classifier, your gradient descent can end up very frequently in these saddle points. And it can, of course, also end up in local minima. And these are all problems you want to avoid. You really want to find the global minimum, right? So how do we know when things will work and when things will not? We would need to analyze that. And so just adding to our lesson so far, neural networks can be trained via gradient descent that minimizes the loss function, where backprop is used to compute the derivatives of the loss. Gradient descent is not guaranteed to find the true solution, even if it exists, is unique and lies within the capacity of the network to model, because the optimum for the loss function may not be the true solution. For large networks, the loss function itself may have a large number of unpleasant saddle points or local minima, which backpropagation, basically which gradient descent, might end up finding. So how can we analyze this? What will happen? Now, in the discussion so far, we found that the training arrives at a local minimum. Let's first start by looking at this. Will the training always converge to the local minimum? And if it does so, how long does it take? Now, this is very hard to analyze for a multi-layer perceptron because the loss functions, as I said, are ugly. But we look at the problem through the lens of convex optimization. Basically, you must have all heard of this old joke. Here's the guy who loses his keys in a dark bar and is found searching for it under a streetlight. And when the policeman asks what he's doing here, he says he's looking here because out in the bar, it's too dark. He can't see anything anyway. So he might as well try to search where he can see things. It's a joke, but you know what? We do that all the time in math and in computer science. We analyze what we can analyze and try to generalize. And so we are going to, this is the streetlight effect. You're looking under the streetlight instead of where you lost your keys. So we will use the streetlight effect. We're going to analyze convex functions. Now, does anybody know what a convex function is? What is a convex function? Anyone? Anybody remember what is a convex function? So a convex function is basically a function of this kind. It's got a bowl shape. And the thing is, if I take any 2 points on the function and draw a line connecting the two, that line will lie either on or above the function curve itself, always. So this guy is a convex function. If I take any 2 points and draw a line, it's always going to be above the curve. This guy is not a convex function. If I took this point and this point and I connected the two with a line, then you see that here is this region where the line actually goes below the curve. And so this is not a convex function. So a simple thing, if you can take any 2 points on the surface and connect them up, if the line lies entirely above the function, above the surface, it's convex, otherwise it's not. Similarly, you can define a convex set. A convex set is one where if I take any 2 points within the set and draw a line between the two, the entire line will lie within the set. So this is a convex set, this is a convex set, this is not a convex set. And so we are going to analyze convex functions optimized over convex sets because these tend to be easier to optimize, to analyze. Now, we will think of what we are interested in is to find out how gradient descent behaves. Now, for an objective function, the objective function has a minimum. Assume for now that it's a global minimum. You start off from some initial point. You say your algorithm is converging if each step that it takes brings it closer and closer to this optimum point. If it does this, then the algorithm is converging. But you can also have this behavior where it comes close, and then instead of actually arriving at this minimum, once it comes close, it can keep bouncing around. So this is jittering. Or you can even have this behavior where instead of coming closer and closer, it keeps getting farther and farther away. So this is divergence. Of these three, which behavior do you really want when you're training your algorithm, your model? You want the first one, right? So does that really happen? For that, we will start off by analyzing a quadratic function, because quadratic functions are convex, and in some sense, quadratic functions are the nicest convex functions. Why? So quadratic functions have this x raised to 2 characteristic. Now, if this exponent was lower than 2, say if you had mod x looks like this. This is also convex. But then here's the thing. If I have, when I'm doing gradient descent, the slope is always constant. If I have a constant step size, then you'll keep coming here. But then once you get here, you're going to keep bouncing around because the step size is constant. So you won't actually converge. If I have a quadratic, then what will happen is that initially you will take large, the slope is large. So even if this in gradient descent, if this step size parameter eta is constant, initially your steps will be large, and then as you get closer, you're going to get slower and slower till you finally arrive at the minimum. This is for things that are x squared. But if you have something that's greater than the power of 2, so let's say I take mod x cubed. This 2 is convex. It 2 is going to look like this, but then it's going to look something like this. It's going to be steeper. And so what this happens is that initially you'll take a very large step because the slope is large, but then it becomes very shallow. And now here the steps will become much smaller, and it will take much longer to get to this optimum. So amongst all the convex functions, quadratic functions are probably the nicest because they bring you to the optimum in the cleanest possible way. Did this make sense to you guys? Why we want to look at quadratic functions? Because they're nice, right? So now, what does a quadratic function look like? A quadratic function looks like, ax squared plus bx plus c, right? And in fact, I'm going to, instead of writing ax squared plus bx plus c, I'm going to write a half over here, simply because of convenience when you take derivatives. Now, if I give you a quadratic function of this kind, a quadratic function can be either like this or like this, right? So when which of these do we want when you're trying to minimize the function? Which of these is the nicer function? First, right? So for that, what will A look like? Is A going to be positive or negative? Anybody? A is positive. If A is negative, then this is going to be, it's going to look like this. So this is the kind of function we are looking at, okay? And now if I give you a quadratic of this kind, do you guys know how to find where this thing is minimum? There's a nice closed form formula, right? You must have encountered this in high school. Do you remember this? It's minus b over 2a, right? So you're going to get, there's a nice closed form formula which will always find you the optimum in one step. But then you can also do this using gradient descent. How? I can start off with some initial guess and then keep utilizing this gradient descent rule. And that too should get you to the minimum, except that it may take many steps. That clear? Makes sense to everybody? Yes or no? Okay, so if I decide to use the gradient descent rule, What is the optimal step size? The optimal step size is one that will get me to the optimum in a single step. Right? That's how I'm going to get to my answer fastest. Okay. What is this value? So to see what this value is, I'm going to look at Taylor series expansions. How many of you are familiar with Taylor series expansions? Are you familiar with Taylor series expansions? Okay, just 5 of you guys, 10. So maybe you should all be familiar with Taylor series. Here is this. Here is what we said. If you had some function f of x, then you could approximate it as around any point x0, you could approximate it as f of x0 plus, what was the next term? Anybody remember? F prime of x0 times x minus x0, right? Plus half of f double prime of x0 times x minus x0 whole squared, and so on. Do you remember this, guys? It must be, okay. So what is this property, right? If I take x0, if I set x equals x0, if I set x equals x0, then you see that all of these guys become 0. And so you get the correct answer, correct? But if I consider x equals x0 and I differentiate both sides, then on the left-hand side, I get f prime of x. This goes away because it's a constant. This is going to, here, when I differentiate it, this term goes away. And I'm going to be left with f prime of x0. And then for the rest of the terms, I'm going to get, something multiplied by x minus x0 raised to some power, right? And so what will happen is that if I set x equals x0, because x minus x0 becomes 0, all of these terms will also go away, and the first derivative will also be the same. So in general, the Taylor series expansion says that the nth derivative at x0 is going to be the same on both sides. And so the series expansion assures you that if the function has infinite derivatives, then the derivatives are going to be the same for both sides. And so the both sides are going to be the same function. And so that's what Taylor series expansions are all about. So if I want to use it, let's say I start off at around this location. If I want to write the Taylor series expansion for this guy, right? I'm going to first write, this is my quadratic. I'm going to write f of x equals f of x0 plus f prime of x0, right? Times x minus x0 plus half of f double prime of x0 times x minus x0 whole squared. This is my Taylor series expansion for f of x. Would you agree with this? Those of you who are familiar with Taylor series. Will I have additional terms? Am I likely to get f triple prime of x0 times anything? X minus x0 whole cubed, for instance. No, because it's a quadratic, higher order derivatives are going to be 0. So if the higher order derivatives are 0, then this thing is exact, right? And so I can actually write this Taylor series expansion in this manner. If E is this quadratic, then I can write E of W equals E of WK plus E prime of WK times W minus WK plus half of E double prime of WK times W minus WK whole squared. And this is exact. It doesn't matter what your value of WK is, this guy is going to be exact. This makes sense? Both are quadratics. Both of them match in the first, second, zeroth, first and second derivatives at any point. And so they're going to always match. This makes sense? Yes, no? Guys, give me some yes or no thumbs ups. I have 3 yeses. Okay. All right. So suppose I use this one instead of this function, and then I compute the optimal point. What is the optimal value of W going to be? To compute the optimal value of W, I just have to take the derivative and equate it to 0. If I take the derivative with respect to W, this first term is simply going to be give me E prime of WK. I'm not going to write the WK, right? This second term is going to give me 2 will come out, 2.5 will cancel, plus E double prime times W minus WK, right? So solving for this, I can say W minus WK equals minus of E double prime inverse times E prime, right? Or I can push this WK over here, and I can write WK out here. And so this is what my solution is going to be. Did this make sense over here? What I just wrote. If I just, right? And so here's what it is. If I try the Taylor series expansion out, this guy is going to be my, the inverse, because remember, if I just take this here, let me erase this. Then I can just consider this, right? If I equate this to 0, when I'm equating the derivative to 0, then I can say E prime equals minus of E double prime times W minus WK, right? Or this, and so this becomes E double prime inverse, right? And so this is what you have. Now consider this, if I have, this is what I write, then this is my solution, right? And if this is my solution, if I were using gradient descent, this is my gradient descent rule. So comparing these two, which is the optimal step size that will give me to get me to the global optimum in a single step? Can anybody tell me, just comparing these two? What's the optimal step size? This one, the inverse of the second derivative. So if you take a step size that's the inverse of the second derivative, then in a single step, you will get to the optimum. Is everybody clear on this so far? This makes sense to everybody. Okay. So now here's my question. I have this bowl. If I take a step size, which is exactly the inverse of the second derivative, I'm going to come to the optimum in a single step. Suppose my step size is smaller than the learning rate and step size, the same thing, right? So they are. So suppose my step size, my learning rate is lesser than this one. What will happen? If my learning rate is lesser than this one, what will happen? Anybody? It's going to go down very slowly, right? If it's greater, what will happen? If it's greater, what will happen? It's going to first overshoot, but then it's going to bounce back and it's going to do that, right? Is there any step size where it will actually diverge? Is there a step size where it will diverge? Yes or no? What is that step size? 2 times, right? If your step size is 2 times the optimal step size, you're going to go here. And then you're going to keep bouncing back and forth. If it's greater than 2 times the optimal step size, you'll actually climb out of the bowl. This makes sense to everybody so far? So here's what will happen. With the optimal step size, you get here in 1 step. If it's greater than the optimal step size, but less than twice the optimal step size, you will still converge, but you'll bounce around. If it's greater than twice the optimal step size, you will actually diverge. So that's for a quadratic, but then assuming Taylor series approximations are valid, even if you have a generic function of this kind, I can always take a quadratic Taylor series approximation to it. and then try to find the optimum of the quadratic Taylor series approximation. And the optimal step size is still going to be the inverse of the second derivative of the function. And you can get divergence if you're greater than the optimal step size, right? So there is no condition. If the learning rate is more than the optimal, twice the optimal step size, you're going to go out of the curve. We just saw that, right? So now that's for a function of a single variable. What if you have a function of multiple variables? When you have a function of multiple variables, then the quadratic still looks the same as before, except that instead of just saying, w squared, you're going to, a times w squared. You will have w transpose A is a matrix times w plus w transpose B plus C. This is a quadratic, which is a function of many variables. The simplest case is where A is a diagonal matrix, and that's enough to analyze. So if A is a diagonal matrix, basically what am I saying? I'm saying that my function, my E, is a function of both W1 and W2, and it's a quadratic of both W1 and W2. So I can write it as minus of half of A1, W1 squared, not minus, equal of half of A1, W1 squared, plus B1, W1. So this is the quadratic for the first term, plus half of A2 of W2 squared, plus B2 of W2, plus C. So this is a quadratic, but it's a quadratic in both W1 and W2, right? This making sense to all of you guys? This is a multivariate quadratic. I don't see enough enthusiastic yeses. Can you give me a few yeses? Okay. And so that's what we've seen, right? This is my quadratic function. And now, if I plot it, this is what it's going to look like. This is a quadratic function. So if I look at it from if I plot it, it's going to be an elliptical bowl. It's going to be something of this kind, where, why does my pen not show up? This is my W1, W2, and the whole thing is going to be a bowl of some kind, right? And so if you look at the bowl from above and you plot the equal value contours, these are all the equal value contours. The minimum is out here. And this is what the overall bowl is going to look like. Now, in which direction is it shallow and in which direction is it steep? In this direction, clearly it's shallow because the ellipses are wider. In this direction, it is steep, right? Because the ellipses are narrower. But then it's actually the sum of two independent quadratics, right? So if I try to find the optimum for this guy, here's what we will find. Suppose I fix, if I take the slices at different locations, it's like saying basically what we had was we had a quadratic of W1 and a quadratic of W2. F1 and F2 are both quadratics. So I had a quadratic of W1 and a quadratic of W2. If I fix W1, W2, this becomes a constant. And so at different values of W2, this constant will change. But as far as a function with respect to W1 is concerned, it's still a quadratic. So it's always going to look like a quadratic against W1, but at different W2s, the height of the quadratic will change because this second term changes. The location of the minimum always stays the same. Similarly, if I fix W1 and just vary W2, then the f of W1 is just an additive constant which which is going to be different for different values of W1. But as a function of W2, it's always going to be a quadratic, and the minimum is always at the same location. So what this means is that if I take many vertical slices, all of these vertical slices will have a minimum right here. If I take horizontal slices, all of the horizontal slices will have a minimum on this line. Did that make sense? If that's not clear, here is my bowl. If I slice my bowl at any of these dotted lines, all of those slices are going to look like this, and their minima are going to be right over here, right on the line that goes through this. And similarly, this guy, is going to have its minima on the line that goes through this one. And so the line that goes through this one, right? So this is good. Now, here's the thing. If you look at the two sets of quadratics, this is a function of W1, this is a function of W2. Each of them is an independent quadratic, right? This term is all the terms that don't involve W1. This is the terms that don't involve W2. Now here, what is as a function of W1, the quadratic is half of A11 times W1 squared. The second derivative is simply A11, right? Here, as a function of W2, it's half of A22 times W squared. The second derivative is A22. So the optimal step size for this quadratic is the inverse of A11. The optimal step size for this guy is the inverse of A22. The two optimal step sizes for the two quadratics are different. That makes sense? Yes or no? Okay. So now, so Siddhartha, if you look at the function as a step, this multivariate quadratic is a function of W1 that has a second order constant of A11. As a function of W2, the curvature is A22. And the optimal step size depends on, if you're optimizing with respect to W1, is going to be the inverse of the second derivative. So it's A11 inverse. Here, if you're using gradient descent and minimizing with respect to W2, the optimal step size is going to be the inverse of the second derivative, which is A22 inverse. The two are not the same. Did that answer your question, Siddhartha? Right. So here's the thing. When I'm using gradient descent, I'm using the same learning rate. I'm just taking a step against the gradient, which means I'm using the same learning rate for every single component of my parameters. Will that work? What do you think? Will that work? Yes, no? Why not? So here's the thing, right? We find that the optimal step size can be different for different directions. So let's take a look at this guy, right? First, suppose I have a wide quadratic versus a shallow quadratic, a steep quadratic. Where will the step size, optimal step size, be larger, here or here? Which has the largest step size? This guy will need the largest step size, right? So that's very clear. Now let's take a look at this guy. Here is a quadratic function. So it has a horizontal direction. It's quadratic against the horizontal axis and the vertical axis. Which has the larger optimal step size? The horizontal or the vertical over here? Which one will have the larger? The vertical will have the optimal step size. So let's say the vertical has some optimal step size, which we get from here to here in a single step. If I use that optimal step size, what will happen in the horizontal direction? What will happen in the horizontal direction? It will diverge, because what happens is that the optimal step size in the vertical direction can end up being more than twice the optimal step size in the horizontal direction. So here I have a few examples. Here in the vertical direction, here the step size we are taking is less than the optimal step size in the vertical direction, but that's already more than twice the optimal step size in the horizontal direction. So in the vertical direction, you're converging slowly to the solution, but in the horizontal step direction, you're overshooting. You're diverging. Here, the step size is further reduced. So the step size is even lesser, and it's much less than the optimal step size in the vertical direction, but it's exactly equal to twice the optimal step size in the horizontal direction. So what happens? While you convert slowly in the vertical direction, you're still sort of oscillating in the horizontal direction. Here I've chosen a step size which is less than twice the optimal step size in both directions. And so you find that you're converging monotonically in the vertical direction, but you're sort of bouncing to a solution in the horizontal direction, right? Here, the step size is exactly the optimal step size in the horizontal direction. But then what happens in the vertical direction, it ends up being too slow. It takes a long time to converge. And here it's less than the optimal step size for both directions. And you can see that while it converges cleanly, because the step size is too small, it can take a very long time to converge. Did this make sense, this picture? So what is the condition that we would have to guarantee convergence? What is the condition needed for convergence? Anyone? What is the condition needed for convergence? Step size is small. How small? How small? Very small? No. It has to be the step size has to be lesser than twice the optimal step size, the twice the smallest optimal step size for all the directions. You check all the directions. Each direction has its own optimal step size, and the overall step size has to be less than twice this minimum. Did this make sense? Over here? Otherwise it's going to diverge. Why twice? Because if it's more than twice, it will diverge. Remember that if I have something, if the optimal step size will get me here, even if it's greater than the optimal step size, so long as it's less than twice, it will still converge. It's only when it's more than twice that it will diverge. That answer you're right? Yeah. Okay, so right. And so again, Aditya, so let's say I'm trying to use the same step size for these two quadratics. The optimal step size over here is going to take me here in one step, right? What will happen for this one in this direction, for this quadratic? What would happen, Aditya? It diverges. That's basically what happens, right? So you want the step size to be less than twice the optimal step size for the steepest side. But that's for a quadratic. But even if you take a generic function, I can always write a Taylor series approximation to it. And then there are many directions, and your optimal step size should be less than twice the second inverse of the second derivative, twice the smallest optimal step size. And so convergence behaviors become increasingly unpredictable as the dimensions increase. For the fastest convergence, ideally the learning rate must be close to you want the learning rate to be as large as possible. Otherwise, convergence becomes very slow. At the same time, it has to be smaller than twice the smallest optimal step size. And so if in the different directions, the optimal step sizes are widely different, then the convergence is going to be very, very slow. So convergence is particularly slow if the ratio of the largest optimal step size to the smallest optimal step size is very large, because the step size cannot be greater than this guy, which means that in the other directions, the convergence is going to be very slow, right? In the ideal case, the optimal step sizes are going to be identical in all directions. That makes sense? Right. Is there a minimum threshold? So you're going to go through all of the directions, and every direction is going to be a different quadratic, right? So you'll have maybe this quadratic in one direction, this one in another, this one in another, the steepest one in the fourth direction. So you're going to pick this quadratic for which the step size is smallest, and the optimal step size has to be less than twice this guy. But that step size is going to be really bad for this quadratic, right? And so we are using the second order, the quadratics, as our base for the explanation, because I can always use a second order approximation and work off of that, and it will still hold. So this was a problem, right? But and there's a lot more on this on the slide deck. Please go over it. But then here's the thing: much of the analysis we just saw was based on trying to ensure that the step size was not so large as to cause divergence within a convex region, right? So it had to be less than twice the smallest optimal step size. Otherwise, even if it converged in some directions, it's going to diverge in other directions. But then, is this actually required? Is this is this necessary? For that, here's the let's look at a more complex function, something that's not quadratic, right? So one second. All right, so do you think this is necessary? Do we have to ensure convergence every time, or is there something else that could be something else that needs to be considered? What do you think? Is convergence always necessary? What is your thought on the process on this problem? Anyone? Why not? Or why? Local minimum. So here. So if you look at an objective function, your loss function can be quite ugly, right? If you always ensure convergence, your initial point may be in some crappy local minimum, and then you'll end up converging to this local minimum. So what you really want to do is that, in situations like these, you really want to diverge, which means that you actually want your step size to be greater than twice the optimal step size. But then if you keep your step size to always be greater than the optimal step size, you're always going to keep bouncing around, right? So what is the solution? Anyone? Did this make sense? That when you're over here, you really don't want to have a step size that's less than twice the optimal. Because if it is, you'll just end up right here. You want to come out, right? So, but if you always keep the step size greater than twice the optimal, you're never going to converge. So what we want is that you want to start with a large learning rate greater than twice the optimal step size, and then it will converge and then it will diverge. But then over the iterations, you want the step size to keep shrinking. And in general, global minima tend to be large, deep bowls. And so eventually you'll find yourself in a large, deep bowl. And there, as you keep decreasing the step size, eventually you'll find yourself in one of these large bowls. And then because the step size has become small enough, by then you'll go to the minimum of this bowl. And then you will actually end up at a better minimum than where you began from. So divergence is not a bad thing, but only in the early steps of the training. So what we really want is to start with a large learning rate and then gradually reduce it with iterations. And so we have these decay schedules for the learning rates. You start off with some step size learning rate, and then you can decrease it in inverse proportion to the iteration number. Or you can have quadratic decay, where you decrease it, in inverse proportion to the square of your iteration number, or exponential decay, where the learning rate falls off exponentially with iterations. And a common approach that you will have in neural networks is that you start off training with a fixed learning rate for a while till the loss plateaus. Then you decrease it by some factor, and then continue till the loss plateaus, and then you decrease by a factor and continue until the loss plateaus, and so on. This schedule is followed because you want such behavior. Right, that's right, Martia. Any questions? Did this make sense? Yes or no? To the rest of you, did this make sense? So you don't need to, right? The weight decay is a very different thing, huh? We'll talk about that in a couple of classes. This is just the learning rate schedule, okay? So can you guys give me some thumbs up so I can actually know that you got it? 20 of those would be nice. Okay. I think I have 20. And so we saw that gradient descent can miss obvious answers, but this may be a good thing. Convergence issues abound. The loss surface has saddle points and local minima, and gradient descent can stagnate on stable saddle points and local minima. Vanilla gradient descent may not converge or may converge too slowly. The optimal learning rate for one component may be too high or too low for others, right? So, Santiago, beautiful question, right? So why, actually, let me give you the second poll. And I'm going to give you only 40 seconds. Be quick. Okay, 10 seconds. Okay. I will stop this right here. Here's what you guys thought. And stop sharing. Can you tell me which of these statements are true? Step sizes that are greater than twice the inverse of the second derivative can cause it to diverge. But this is not necessarily a bad thing. On the other hand, you don't necessarily require decaying learning rates. If you happen to be a quadratic, a fixed learning rate would work just fine, right? Only the first statement is true. Anyway, so decaying learning rates may divergence causing learning rates may not be a bad thing for ugly loss functions. Decaying learning rates provide a good compromise between escaping poor local minima and convergence. But all of these issues arise because, as Santiago just pointed out, we are using the same learning rate on all parameters. But why are we doing this? Why are we using the same learning rate on all parameters? Anybody want to guess? Why? Why are we using the same learning rate on all parameters? Anybody?
If it was different, you would like duplicate the size of parameters that you need to estimate.
It's not really that. The issue is that we don't really know what the optimal learning rate is for any dimension, right? So ideally, we would use a different learning rate for every direction, but when what is it? So let's take a step back. Our problems arise because of requiring a fixed learning rate across all dimensions because we're using gradient descent. Let's try releasing this requirement. And there have been many algorithms which have been proposed that release this requirement. Algorithms that use derivative information for trends but don't follow them absolutely, like rprop and quickprop. And here what we do is we keep track of the optimal learning rates for each direction independently. And how the real challenge is in figuring out how to keep track of these things. So I'm going to talk about one algorithm. There are other algorithms over here that I was planning to cover today, but I won't because we are running behind. But rprop was one very famous algorithm called resilient propagation. It's a simple algorithm which is followed independently for each each component. At each time, you just say, so here is the simple idea that you use. I have some function, right? So let's say I came from here and now I'm just going to take a step. I'm not speaking of step size. I'm not speaking of learning rate. I'm speaking of the actual length of the step. And I take a step over here. So how do I know that when I came from here to here that I've taken a step in the correct direction? How can I know that I'm going in the correct direction? Anybody? What is the immediate clue? Just looking at this function. It's not just the loss is decreasing, right? Because if I went from here to here, does this mean I should continue in the same direction? The direction, the slope, the sign of the slope is the same. Here I'm not diverging, Siddhartha. I've actually gone closer to the optimum, right? So the sign of the slope is the same in the two cases. So here is a simple thing I can do. I can start off and say, I'm going to take a step in some direction based on the initial slope. I check the slope again. If the sign of the slope is the same, now I'll take an even larger step. Then I check the sign of the derivative again. Here the sign of the derivative is negative. Here too it's negative. And here too it's negative. So it means I'm going in the correct direction. So I'll take an even larger step. But then when I take an even larger step, even though the loss has decreased, what has happened over here? What happened between these 2 points? Anybody? The sign of the derivative changed. So what should I do? I can go back and then decrease my step size and take another step, right? Simple algorithm. This is our prop. Did this algorithm make sense to you guys? Yes or no? Right, very simple. And you do this independently for each direction. And so that's our prop. Select an initial value and compute the derivative. And the derivative sign of the derivative tells you which direction to go. And then take a step against the derivative. You're going to end up at a new point. Then you check the sign of the derivative at that point again. If the sign of the derivative has not changed, then you multiply your current step by some term alpha and take a longer step. You get to a newer point. Then you check the sign of the derivative again. If it's still the same sign, then you multiply this step size by alpha again. So that gives you alpha squared times the initial step size. And then you take that step. And then you're going to end up at a new location. Then you check the derivative over here. You see that the derivative of the sign of the derivative has changed. So that means you've overshot. So then you go back. And then whatever step size you had over here, you multiplied by some beta to reduce the step size. And you got over here, which brings you here, and then you continue as before. Did this algorithm make sense, the whole thing? Very simple. This is our prop, resilient prop. And yes, it can get stuck in local minima and such like, but it turns out that it's actually quite resilient to local minima and such like, and works really nicely. So here is the overall R prop algorithm. For each parameter, you just compute the derivatives. And the derivative is going to be computed using Backprop, right? And then once you compute the derivative, you just check the sign of the derivative. If the sign of the derivative is consistent between the previous step and the current step, then you increase your step size by some factor alpha, and then take a step in that step size. On the other hand, if the sign of the derivative has changed, then you go back, multiply that step size by some compression factor beta, so that instead of taking this long step, you take a shorter step, and then continue the process. That's it. So the pseudocode may look complicated, but did the whole thing make sense? Yes or no? Right. So there are different things, right? You can try to change the sign and so on, but the simple thing is to just go back and take a smaller step. There are different ways of dealing with it. There are other heuristics that people have used. So it's a remarkably simple first order algorithm that's frequently much more efficient than gradient descent and can be competitive against some of the more advanced methods that we use today, and makes minimal assumptions about the loss function. It makes no assumption about convexity. It really works. And so here's my third poll for the day. And I don't think I'll have time to get to the fourth poll. Okay, 10 seconds. Well, I think you guys are done. I have only 180 people. This is what you thought. Stop sharing. Okay. What did we do? Answer, guys. Which was the correct answer? 2. 1, right? Look, what we did was, look at this. The way we defined it, if you overshot, you found the sign change. So you went back to the earlier point. And then whatever step size you had over here, you multiplied it by some shrinkage factor beta, so that you ended up with a smaller step size, and then took the next next step, right? And so our correct answer is that you revert to the earlier estimate and take a smaller step. The second one is also a feasible heuristic. It's a little more complicated. You have to keep track of more things, but yes, people use it. So Rprop really works. There were other techniques like quick prop, which was invented by Scott Fahlman and of LTI, which uses Newton updates with empirically derived derivatives. And this is quick prop is an upgrade on Rprop and is even more efficient and still one of the fastest training algorithms today for many, many problems. So the story so far, gradient descent can miss obvious answers. This may be a good thing. Vanilla gradient descent may be too slow or unstable due to differences between dimensions. I have not gone over second order methods, but they are in the slides. They normalize the variation across dimensions so that they try to make the curvature the same in all directions. But they need an Hessian inversion and they are complex. You can have decaying learning rates to improve convergence. And methods that decouple the dimensions can improve convergence. So any questions? Questions? No. Okay. So here's the thing. Here's a closer look at the convergence problem. With dimension-independent learning rates, the solution will converge smoothly in some directions and diverge or oscillate in other directions, right? So let's do something. Let's look at a heuristic. Let's keep track of the oscillations. In directions where it's converging slowly, we will increase the step size. In directions where the directions keeps flipping, right? Like we saw in the case of Rprop, the direction in which we want a step can keep flipping. So in directions where the step sign of the step keeps changing, like over here, that means our step size is too large. So in these directions, we will decrease the step size. And so we can actually look at how the updates behave, and based on that behavior, we can modify the step size. That makes sense? This is a principle we are bringing forward from Rprop. Right? That makes sense to all of you guys. I just see a single yes. What about the rest of you guys, right? So this is what we will do. But then how do we do this? To do this, we have something called momentum methods. You want to do this without explicitly looking at whether signs are changing or not. And so that's where momentum methods come in. I won't have time to go over this today, but we're going to revisit momentum methods in 2 lectures because it's more important once you look at stochastic gradient descent. But do go over them in the slides, they're in the quiz. What they do is maintain a running average of all past steps. If I maintain a running average, the directions in which the convergence is smooth will have the running average will be large. In directions in which the derivative keeps changing sign, the positives and the negatives will cancel out because the running average of a series of positive and negatives is going to be close to 0. And then you update with the running average rather than the current gradient. Does this make sense? So basically, in some direction, if my derivative is always going forward, then it means that I'm going in the correct direction, so I can keep increasing the size. In other directions, I keep going back and forth. It means I have to decrease the step size, right? So if I look at the running average of the derivatives over here, the running average of the derivative is going to be consistent. Whereas if I look at the running average of the derivatives out here, Some are positive, some are negative. The net running average is going to be small. And so that is going to give you a smaller step size and these directions. That is the basic principle of the momentum method. This makes sense? Yes or no? Right. And so those are momentum methods. We will cover them in a later lecture. They are there on the slides. And yes, Anya, we will look at momentum methods and Nestrov's accelerated gradient. I just wanted to convey the basic idea today. I'll stop right here. I sort of fell short of how much I wanted to cover, but we should be good.